Welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Professor Jongbae Hong from Seoul National University. And our scientific host today is Sergey, and I ask Sergey to introduce our speaker.
Yeah, okay, thanks. Welcome everyone to yet another PCS seminar. We are now getting more and more in real life again instead of our Zoom sessions. So it's a pleasure to have today Professor Jongbae Hong with us. And let me give you a few data on our speaker. He did his undergrad studies at the Seoul National University and then moved to the States, where he did his PhD in '82 at the University of Georgia. And then he moved to, he was at various places. He was at Kondo University as an assistant professor. Then he moved to Seoul National University, where he became full professor, rising through the ranks. But he was also a visiting assistant professor at the University of Georgia. And he was as well a guest scientist at the Max Planck Institute for Physics of Complex Systems in Dresden, which is actually, we have met there. Okay. And but I think Henning was already gone by that time. This was 2009 until 2010, right? And then our speaker also was a collegiate professor at Postech at the APCTP in Pohang. And then he joined our center from 2015 to 2017 as a senior researcher, and then moved on for a position at Incheon National University, where he stayed until 2020. And then he moved back to his alma mater at Seoul National University, where he is now Professor Emeritus. And he had a lot of other activities which are reported. I maybe want to mention that he was the associate dean at the Seoul National University, and he was also involved in the activities of the Korean Physical Society, but also of the Center for Theoretical Physics in Trieste. And there are other things maybe which we don't have time right now to talk. He has patents, which is quite impressive for a theoretician, I would say. Actually, 4 are listed here. And he is mainly doing research in the area of fractional quantum Hall effect, but also coherent tunneling correlated systems, so more broadly, strongly correlated electronic systems. And today he will talk about gate voltage-driven quantum phase transition in quantum point contacts. Jongbae, the floor is yours. Let's welcome our speaker.
Long and very nice introduction. Okay. It is very nice for me to come back to IBS, not PKS, PCS, sorry, as a seminar speaker. Okay. My title is Quantum Phase Transition in Quantum Point Contact.
If you want, you can use this symbol.
Oh, it's okay. Today's title is related to the revival of the Kondo effect from about 2000. Okay. Then revival means the Kondo effect is non-equilibrium Kondo phenomena in various mesoscopic systems, such as quantum dot, and quantum point contact, at which my talk will focus on, and a single molecule transistor, and adsorbed magnetized atom on metallic substrate. Okay. Experimentalists measured tunneling conductance for these systems. Line shapes something like this. The schematic of these systems are given expressed by two metallic reservoirs and one mediating on the atom at which the strong Coulomb repulsion exists. Therefore, U much larger than bias, source drain bias. So this spin cannot, double occupancy is forbidden. So the only way to make a coherent current is make a Kondo singlet and co-tunneling and the changing pattern and the co-tunneling, something like that. Yeah. So therefore, this is called the steady state non-equilibrium. Okay. Today's subject is the gate voltage dependent DIDV line shape quantum point contact. From this line shape, can you imagine a certain phase transition? Maybe not, not yet. I show there is just phase transition. A sufficient condition of phase transition is the existence of a spontaneous symmetry break. If this one exists, that guarantees continuous phase transition. Okay? In fact, there are two different points of view in understanding the physics of quantum point contact. Some people say this zero bias peak is not Kondo peak, okay? But some other people say this is Kondo peak. Okay? There is a localized spin exists. Okay? So I follow the Kondo. Follow the work of spin density function theory calculation done by Rejek and Meyer, reported in 2006 in Nature. They observed a bound state below the Fermi level. Yeah. That means there is a localized spin, which make a Kondo phenomena. And they also observed the position change of the localized spin by changing the gate voltage. Gate voltage means side gate voltage. Okay? At higher gate voltage, the localized spin exists at the center. Okay? So that means left side Kondo coupling strength and the right side Kondo coupling are same. Okay? But in the low region, low gate voltage, this localized spin exists away from the center. Okay? Because this is the equilibrium calculation, so they show two, but if you apply bias, one may disappear. So we can consider only one localized spin in this system. Okay. Let's see the role of gate voltage in QPC. So as I show you here, they observed this change. That means there is a spontaneous symmetry breaking if we decrease gate voltage from high to low. Okay? At the high gate voltage, the localized spin exists at the center, so left-right Kondo coupling are same, symmetric, but at the low gate voltage, they are different. So they may be at the transition point. Okay, from here. So the gate voltage may induce a quantum fluctuation, and that gives a spontaneous symmetry breaking in the left-right Kondo coupling. That gives a continuous phase transition. The purpose of this study.
I'm sorry, can you clarify what's the physical nature of having bound states in the middle of quantum point contact?
In this one?
Yeah.
What does this means? Okay.
Spin or electron is localized in the middle of quantum point contact.
Oh, why somewhere here? Actually, that I don't know. It is the result of spin density functional theory calculation. But this one means if you consider Kondo physics, the localized spin is below the Fermi level, so that is the bound state. So the detailed things I don't know. That's not my topic.
But maybe I can just ask, so why do you think it's not clear, or what is the difference?
No, I mean, I'm curious. Yeah, to have conductivity, you need to have localized spin,
Right.
usually below Fermi end.
Yes.
So I just want to know what's the nature of having bound state inside the quantum point. So it's a diabatic constriction. Potential usually is parabolic.
Maybe you are asking this one. Okay. If you see this one, this is metal. Yellow is metal. So if I change the gate voltage, increase gate voltage, it becomes narrower and narrower. There was some electron between this constriction, but if you increase the gate voltage, the electrons go away, and finally only one remains. That is the localized spin. That you ask.
Question: always localized state is on non-degenerate?
No.
But the Kondo is we are asking the
At the localized state, the Coulomb repulsion is strong, so only one spin can exist.
but there are
No double occupancy.
sometimes the multi-channel is not impossible. Always single channel
Channel is only two: the left channel and the right channel.
localized state is only one.
Yeah, unlocalized.
In your experiments, out of experiment setup is localized state is only one. Is enough. Wow.
The experimental result is only this one. So there could be another localized state that gives also Kondo coupling to left and right. So and make a coherent current. But theoretically, we need to consider only one. Yeah, that describes the physics. Even though other localized spin exist, that can also make a similar kind of coherent current. I mean, this result may be same. So
Can I think that the calculation that here used DFT, the density function theory calculations, and I don't know exactly what the ingredients are there, the calculation, but is there any other method, theoretical model, or for example, non-interacting model, which they can reproduce this calculation?
No, because this is strongly correlated systems. Non-interacting cannot explain this correlated system.
I see. State this density function theory calculation is only one which they describe this quantum contact model.
Probably. Yeah. There are some papers, but all use similar kind of spin density functions. Yeah. So the only dynamical data is this one, okay, for the quantum point contact. Therefore, one must reproduce these lines perfectly to reveal the secret of quantum point contact. Okay. Reproducing these lines is not simple. nobody nobody have done. That's my work. So after reproducing this line shape, then one may say the phase transition by analyzing the parameters that reproduce the line shape. Okay, that's my work. So first, we need the theory for tunneling conductance. This is well known Meyer-Winkelin, the formula for the coherent current. Okay, so let me skip this. And this gives tunneling conductance formula for this like simple form. This low. Oh, okay.
Yeah. Good old.
This is so-called local density of state. Local means at the mediating site. Okay? And this local density of state is expressed by imaginary part of on-site retarded Green function. Therefore, theoretical issue is finding this one. This work. So, Green function technique. There are two kind of Green function technique. This one I call the Schrödinger picture because this is state vector and Hamiltonian. But the similar formula can be written like this. You just change the Hamiltonian to Rubin operator. Okay, but here Rubin approach. This is the basis operator. In this Hamiltonian approach is the state vector. Okay. I chose this one because the first step is determining a complete set of basis vectors. But if you use this Hamiltonian approach, you cannot determine a complete set of basis vectors. That's very difficult for the correlated system. But correlated system, this operator is possible. Okay, it's very interesting. So my system is like this, and the equilibrium Hamiltonian is two reservoir Anderson impurity model, left reservoir and right reservoir, and on-site Coulomb repulsion, and then this left hybridization and the right hybridization. Okay. So this like this. D upspin on T is equal to e to the I Rubin operator T and okay. Then this means H D E1 and then one more and then this produces linearly independent basis operators to describe this. But that is very complicated. But if you consider this one, I can make a working Rubin space. Working Rubin space. Working means I neglected some unnecessary and complicated processes. Okay. That gives this one. Okay. This means upspin just annihilate at this point. Okay. Then for hybridization, this. This means when upspin annihilate at here, downspin moves coming in or going out. Okay. To this way and that way. Then this group C is describing the state of reservoir, left reservoir and right reservoir. That's all. Now I must construct a Rubin matrix. Okay? It's infinite by infinite. I arrange the basis operators like this. Okay. Then calculate this one for the basis operator. Because this is a non-interacting reservoir, I have a diagonal, only diagonal terms. Okay. That helps me very much. And all things are complicated, but anyway, straightforward. This matrix N is composed of nine blocks. Okay. So this infinite by infinite matrix. Anyway, we need the inverse. Okay. Generally, the inverse matrix of for the infinite by infinite is impossible. But in this case, the infinite dimensional part is here, so it's diagonal. Therefore, we can reduce this infinite by infinite matrix to finite by finite matrix using this matrix reduction technique developed by this person. So this 9 block is written in this form, and I wrote here this column vector and the right side, I said, like this. Then I have three independent equations from this matrix equation, and then I eliminating this CKL and the CKR, and the remaining thing is this one. Okay, so these are 5 by 5 matrices. Okay. Whether we can get the inverse or not depend on the inverse of the infinite by infinite part, this one. But in our case, it's a diagonal matrix, so it's just easy. Okay. I have a reduced forms, reduced matrix M. It's composed of PD part. PD is the central part, plus this part is actually this separate matrix. Then my Green function, on-site Green function, is given by this one. And then local vector state can be represented by this reduced matrix inverse. Okay. So actually, this the form of matrix element is something like this. Here, the expectation value is for steady state. Okay, but this one is just equilibrium. Okay. This part, this U element, this is the effective Coulomb interaction due to screening by incoherent electrons. But these are all coherent part. This gamma LR S and S means symmetric, and this is the anti-symmetric. If you analyze these operators, then that shows this one is this movement plus this movement, and this one is this movement minus this movement. But our case is so-called entangled state tunneling. Okay, left Kondo coupling and the right Kondo coupling. It's linear combination of the two. So if the bias is applied, then the motion is unidirectional. Therefore, this vanishes and only one remains. So, this case, the symmetric case is equal to anti-symmetric cases. And these operators, there are 6 operators. 6 operators means third order hybridization. I will show you graphically in the next graph. But the steady state flow needs fourth order hybridization. I'll show you that thing. Therefore, fourth order means we need 8 operators. Okay? But in gamma representation, only 6. So additional two operators must come from the definition of non-equilibrium expectation. Actually, non-equilibrium expectation depends on case by case. It's not like equilibrium Gibbs ensemble theory. It's non-equilibrium is not well defined. It depends on case by case. So in this case, if I add these 2 operators, that gives gamma L described this is B up and L down on the singlet, and then this means quaternary. This appears different and appears upstream right side. That is quaternary. Then this one make a singlet formation, and disappears, and the spin change. From here to here is described as spin change. Here the hybridization left side is cubic, but the denominator has square, so it cancels only. This one is the hybrid. If you see the only hybridization, it's proportional to 1. Okay, we to the 1. In case of gamma R, to have this kind of steady state, okay, this and the final state are same. Okay. Then it's repeated.
Why spin flip is allowed? Why you always make spin up disappears and spin down appears?
Because from here to here, this is quaternary. Quaternary together.
Okay. Thank you.
Upspin, change it down.
So the final picture as a spin exchange.
Spin exchange, yeah. From here, this means this state down, up, and changing exchange down, up, this one. Okay. So let's return to the original state. This in this case only one string moved. Okay. The gamma R described, but here gamma V tilde L and the V tilde R square, and the denominator is this one. So V tilde L. If you see only the hybridization strengths, they are same hybridization strengths. Then what is the where the difference come from? It's here. It's a spin exchange. The spin exchange is this left side, and this spin exchange on the right side. Okay. If in this case, in this asymmetry case, this Kondo coupling is stronger than this side, then gamma L is larger than gamma R. Okay. So that is the difference.
So can I question that be sure I understand correctly that the bottom figure, if I understand correctly, that this calculation by the DFT by varying the gate voltage, right? In this, your schematic figures describes the effect of the bias between source and drain.
Yeah. So strain bias.
Yes.
Okay, but this has nothing to do with the spin-based functional theory. Spin-based functional theory has been finished already.
I see.
So this is the whole my story. Okay. What I show you is only this form, operator form. I cannot calculate this one. The real calculation, not only the operator distribution. Then I can understand what happens because the operator describes the dynamics. So the dynamics is something like this. Okay. So anyway, to obtain the tunneling conductance line shape, we have to determine the matrix element and the coefficient that are cubed. I cannot calculate the expectation, but anyway, we have to determine. How can I determine these matrix element and the coefficient? The atomic limit analysis tells us the guide. Atomic limit means okay. Line shape is the central peak and the side peak and the Coulomb peak here. Side peak and the Coulomb peak here. The atomic limit means this is speed and one delta function here, one delta function here, one delta function, and delta function. And the spectral rate, only spectral rate and the position of delta function. So this atomic limit analysis says that the positions of two coherent side peak is given by gamma L and gamma R. Okay, square plus square root divided by 2 and square root. And the spectral rate of the side peak is given by gamma LR. I told you S and A is same. And the spectral rate of the zero-wise anomaly is given by gamma L and gamma R, only gamma L and R. So if I fit the side peak into by adjusting, by controlling the gamma L and gamma R. So when the gamma LR controlled the broad peak of this one. Okay? But the position is determined by gamma L and R. And this one, real part of mu term is in the atomic limit is just mu/4, and the self-energy coefficient is 1/4. This is standard value. Okay? Real situation is some deviation from 0.25, and the delta 33 is 1. And also, I found that this element controlled the relative height of the GB zero-wise anomaly and the side peak. Let's control it. And UJ minus controlled this local minimum and this. Okay. So using this guide, I can choose the matrix element very well. So the values of matrix element for gamma LR is this, and gamma L, gamma R, and U like this, and beta something like this. then I got the local density of state, this form, and this times this gamma tilde gives tunneling conductance and shape, and the result is like this. Okay, the black lines are experimental data, and the colored my theoretical result. Because this experimental result, black lines, somewhat asymmetric. So I did the right side. Okay? Right side is well fit. So this, and also the local minimum, left, right, and the left, but it's somewhat asymmetric and fit the maximum point and the area of generalized anomaly. Okay? So if you see the right side, the fitting is quite good. The natural order parameter is the difference between the gamma L and the gamma R. The Kondo coupling strength difference between left and right. Okay. So here actually this red square is my data, theoretical data, but this black square is just for your eye, guide for the eye. Okay. Only data is red. So here the order parameter exponent is 0.373. It's not enough. I need another evidence, important evidence of phase transition. Okay. Yeah. To do that, yeah, I must ask me, does the GBA, this generalized anomaly, show the equilibrium Kondo physics? Because the phase transition is actually the equilibrium physics. So this guy, Haldane's work is hard to read. 1979, he published a paper for the quantum dot, and the Kondo temperature is proportional to the exponential pi times epsilon 0 is the bound state energy divided by gamma. So again, this Raja and Meyer, 2000 density functional theory people, they show that this epsilon 0 behaves like this. So this is transition region. The transition region is nearly linear. Okay? Red one is important because this is symmetric data. So this describes this is, and then this is linear. So linear on wave quantity is linear in this one. So if I take a logarithm for the temperature, then that is just proportional to the gate voltage difference from the causal. So my data for log linear plot is straight line, and other experiment for the quantum point contact is this people that people they also show this linear and linear, and this Cambridge people also it's linear. I showed you this.
So can this gradation be interpreted as a fluctuation dissipation?
Sorry.
Sorry. So is that related to a fluctuation dissipation theory that you can explain it in terms of equilibrium?
Fluctuation dissipation. Fluctuation dissipation for what?
When you study the transport through the system in the steady state, but it's a non-equilibrium steady state. And your conclusion is that you can explain it in terms of the equilibrium physics of the system. Is it the non-stationary?
Oh no, only this one.
Only this part.
Yeah. I know why I show this. Okay. Again, atomic limit analysis says the GBA spectral rate is does depend on gamma L and R. So only gamma L and R has a spin exchange. Okay? So spin exchange is equilibrium Kondo physics. So that means this one is completely non-equilibrium steady state. Yeah, therefore, we can study this one, the GBA peak, to study the equilibrium phase transition. So I obtained the GBA energy using this form. Okay, this energy times local density of state, and then from 0 to minimum, 0 to this minimum. Yeah. That's it. Our result. In the log plot, they showed this nice straight line. That means this energy, GB energy, showed power law, or this side and this side. Index is different. Okay, anyway, power law behavior. In the linear plot, I numerically show that this power index is 0.668 and lower than the critical point, and larger than critical point. The index is 1.198. What this means to say, the modern classification of quantum phase transition. I saw this one from internet because a long time ago I studied the quantum phase transition, but modern means recently they changed the terminology. Okay. All time we said the first order phase transition, second order transition, third order transition, something like that. But modern means first order transition has a latent heat, like this, latent heat. And then all other things they call continuous phase transition, no latent heat. Okay. See, what is the first derivative and second derivative? The initial function is Helmholtz free energy, okay, minus KT log G. So dimensionless one is log KT and minus log G. Okay. This is the beginning point, starting point. First derivative is the first derivative of Helmholtz free energy. It gives average value for energy. And then the second derivative is give the capacity. So in case of continuous phase transition, if this energy is something like this, is power law, or then the second derivative is going up and discontinuous, up and down. The first derivative is log G is something like this, and the first derivative is discontinuous. Okay, this is a so-called modern classification. according to this terminology, my result is this is the first derivative of free energy. Okay, so shows this power law behavior. Okay, and the second derivative at this point vanishes because this index is larger than 1. Okay, first derivative, the second derivative of this one is still 0.198. So if Vg approaches 9, vanishes 0, approaching 0. But this slide is less than 1. Okay, so derivative of this one, and you move Vg to 9 and diverge. Okay, so the second derivative is discontinuous. Okay, this proves the existence of the continuous phase transition. Okay, my last conclusion. I studied 2 reservoir quantum impurity system under bias as a model of quantum point contact. Okay. I identified that the gate voltage induces spontaneous symmetry breaking. That is the result of spin density functions, not my work. But I realized that there is a spontaneous symmetry breaking by gate voltage, side gate voltage. And I reproduced experimental tunneling conductance line shape nearly. Okay. Then I analyzed the parameters and observed the gate voltage driven conductivity condition for first time. So lastly, I identified the other parameter of phase transition and its critical exponent 0.373 is the mean field order parameter exponent is 0.5. The energy of GB energy was analyzed to prove the existence of a continuous phase transition. QPC. Thank you for your attention.
Okay, thank you, Jongbae, for this nice talk. We'll have time for questions. Yes.
Related to the experiment, is there any result in the temperature dependent of the conductance?
Of course, experimentally.
Experimentally, measure the Kondo temperature is appeared zero on this day.
Oh, indeed. This one.
Yeah. I went.
It's 0.7 anomaly of NV extract on the temperature.
Disappeared the ceremony.
Jongbae anomaly is disappeared.
How did you just measure the conductivity and the move? How to,
They measured many things, just really so-called conductance something like that. And not gate voltage. No, not temperature. This is gate voltage. This so-called there is 0.7 anomaly. The point contact is actually well known for 0.7 anomaly. Here. This is temperature, increasing temperature.
it's also like
Yeah. And Okay, cool. Okay, I think you are asking this, the temperature dependence of this peak. This point. Yeah. If the temperature is bigger than Kondo temperature, then this disappears. Yeah, it's just flat.
Okay, we have a question from Amnon Aroni. Amnon, please go ahead.
Yes. Did you or anybody else attempt to map this problem to a field theory? And can one associate the exponents you find to some universality class of quantum phase transitions?
The question is somewhat difficult to me because I have no idea about field theory, and you are an expert in statistical mechanics, but I am rather away from your line. So those things actually I have no idea.
Okay, thank you.
Okay, more questions? Yes, Anton, please.
Don't understand. So all your results can be applied to Kondo system based on quantum dot embedded between two electrons.
Yeah.
So why do you choose quantum point contacts?
Only quantum point contact show the gate voltage dependent line shape. Only this one.
In print, my question is, since these two side peaks in some sense should be correspondent to the on-site Coulomb potential plus tunnel barriers. And in quantum dot system, again, with the split gates, you can control this.
Yes, but in this quantum dot case, they don't show this like very clear side peak. Okay, see, this one looks like a single peak, but if you apply magnetic field, there is some deviation. This magnetic field and the position of the central peak is not this one. This much deviation. And if you apply magnetic field the other way, is this. Okay. This means there are three peaks altogether. But this is a one single peak. They show this peak. If you apply magnetic field, it just follow this line. So it's very interesting. This three peak means this. In my understanding, these three peak are just very close. And this peak is this one. This one is this. So this is single peak.
But in quantum dot also, central peak should be associated with the Kondo effect. So it should be Kondo temperature, and two peaks should be associated with the occupied level and level for double occupation. In principle, in quantum dot system, you should control position of these peaks.
You're right. You're right. Here they explain that kind of thing, but I don't know. In case of probably the quantum dot case is something like this. These peaks are very close, so it looks like a single peak in quantum dot case. So I cannot analyze the phase transition like things like this quantum context.
Also, for answering, because I know that for quantum point contacts, there is alternative theory which can explain reservoirs anomaly and 0.7 anomaly even without Kondo impurity. It's just about.
Yeah, I told you there are two points of view, but I think this will win. Okay, because this cannot explain this line shape. Only they say this one. Okay, it's even with the non-Kondo or effect they show this one, but if you see all these things, then Kondo may be right.
Okay, more questions? Yes, please.
Yes. So you said that there is a slight asymmetry between the left and the right side peak, right? So when you were fitting your results,
That's right.
so the DIDV curve. So the when you were fitting your results, yes. So could you explain this asymmetry in the position of the two peaks, which is very tiny, by some higher order processes? So in a similar way that you describe the position of the peaks themselves with the lowest order, which you said was the 8th combination of creation and annihilation operators. So could the asymmetry be explained with the higher order? Yes, so here. Yeah, so this explains the kind of line shape and the position of the zero bias anomaly and the two side peaks, right? But
yeah, I said zero bias, the spectral rate of zero bias anomaly is given by gamma L and R, and the position of a side peak is also only given by this L and R. So if I control L and R, then I fit the side peak, okay, and the broadness of side peak is controlled by this gamma L and R. And but this side zero bias peak spectral weighted automatically. If I match the position of the side peak, that means I determine this gamma L and R. So if I determine this one, this GBA spectral weighted automatically determined. So it's quite simple, not that complicated. Fortunately.
Okay, more questions? If that's not the case, let's thank Jongbae again. Thank you very much. And there should be again some food at some point.